Thanks for downloading a 3CR podcast. 3CR is an independent community radio station based in Melbourne, Australia. We need your financial support to keep going. Go to www.3cr.org.au for more information and to donate online. Now stay tuned for your 3CR podcast.
Welcome to another episode of Lost in Science. Once again, it is so much science that you will not believe what is going on. We have a fantastic show prepared for you tonight. With me once again, we have Catriona Nguyen Robinson. Hello, Catriona.
Hello, Chris. Thanks for having me.
It's always great to have you here. I hope you've gotten over kind of your, the buzz of your PhD submission, but not too much over it.
Yeah, it's still fresh in the memory.
Yeah, those scars take a long time to heal. Yeah, definitely. And you've got some current science for us today, I believe.
I do indeed. I'm going to be talking about DART.
Oh, not the Dart, to quote that ad from the Go-Go Mobile ad from years ago. No? Okay, no one. People can look that one up. Yeah, so just remind us, what is the DART? Okay,
so essentially, if you think about it, if a planet-killing asteroid hurtled towards Earth, the whole planet can't exactly just dart out of the way. Just had to throw that pun in there. So that's why we need planetary defense mechanisms, and that's where DART comes in. So this is NASA's Double Asteroid Redirection Test, and the DART mission has shown that it's got what it takes to defend us. So DART is actually the first ever space mission to demonstrate asteroid deflection by kinetic impact. Essentially, what that means is that it can knock the asteroid to change its speed and its path. And what's important is that this test has been done now and it's performed way before there's any actual need. So we don't actually have a threat of asteroids. We wanted to just test that we could do it.
Fantastic.
So, yeah. Stu talked about DART's launch last year, but after 10 months of flying in space, we've finally got some results, and that's what I want to talk about today.
Brilliant. Well, it's really good to know that we have some success in this area and that we have some preparation so that we're not going to be like getting together Ben Affleck and a bunch of oil drillers at the last moment and shooting them up to try and, like in the movie Armageddon, that technology has moved a long way from the late 90s, I think, or early 2000s, whenever that was.
Well, even Don't Look Up, which only came out last year, where we're hoping for a situation not like that. And I'll just leave that there. No spoilers.
Yeah, exactly. Excellent. You mentioned Stu. Stu also will be on today's show. He has an interview coming out with Tien Huynh from RMIT University, talking about some new research that they're undertaking to find out a way to grow plants in space. I believe the plan is to grow plants on the moon within 4 years. So, I don't know if you've ever tried to grow plants on the moon. I've certainly never tried to grow plants on the moon. I don't imagine it would be very ezy.
Yeah. Lacking nutrients, oxygen, water, like all those good things.
All this stuff. I don't know exactly what their full plan is, whether they're just going to plant something in the soil, a la The Martian. Or, whether they've got some more controlled system arranged. But we will find out. Stu will find out for us, and we will hear all about it. Right, so fantastic show coming up. Stay tuned, and on with the show.
So DART's trip was one way, and NASA wanted to test whether it could successfully navigate a spacecraft to intentionally collide with an asteroid to deflect it. And that's a technique known as kinetic impact. So DART's target was the binary asteroid system Didymos, which means twin in Greek, and kind of explains the word double in the mission's name. It's not trying to hit two asteroids, it's just targeting a system that has two asteroids.
Right, okay, yeah.
Yeah. So, as the name suggests, there are 2 asteroids in this system, and the spacecraft targeted the smaller one, which is called Dimorphos, and it's a small body, just about 160 meters in diameter. And it orbits a large asteroid called Didymos, which is 780 meters. And neither of these 2 asteroids pose a threat to Earth, but all of this is about whether or not we can do it. So, can we deflect it?
I mean, I guess there was a bit of a worry that if they're going to deflect it, that they would make it pose a threat to Earth. That would be the worst case scenario.
I guess so, but I mean, we can't really have that much of an impact on it. Like, you know, they were just hoping for, you know, a little bit of a knock.
Yeah. Now, can I just ask though? I mean, so I mentioned the movie Armageddon in the intro there, and there was, of course, Deep Impact was another one around the same time, where the plan was to try and, I guess, deflect or destroy asteroids using explosions, and I think usually nuclear explosions, what they do in the movies. This is not that, is it? This is a different situation.
Yeah, this is like quite gentle, I guess, in comparison. It's really just if you push into the asteroid, what the researchers and the scientists were hoping to do was just knock it a little bit off its orbit. So before this, so several weeks ago, 3 weeks ago, before, you know, we did anything, the smaller asteroid, so Dimorphos, was orbiting the larger asteroid, taking about 11 hours and 55 minutes. So essentially what they wanted to do is see, can we just knock it to get it faster, slower, something. So they knocked it and shaved off 32 minutes, plus or minus 2 minutes, which is about 1% of the time that it takes to go around. And really, to be successful, they actually didn't really need that much. They would have considered a change as little as 73 seconds shaved off the orbit as a success. Before we could actually measure how much out of the orbit it had been knocked, scientists were predicting at least 10 minutes. But yeah, getting 32 minutes is pretty good.
So, like, I mean, so what you're doing, you're crashing one thing into another thing. Mm-hmm. In this case, you got this small asteroid, Dimorphos. Yeah. And then you're crashing something much smaller into it, but at very high speed.
Yes.
You know, it sounds like we should have had a pretty good idea of what it would do, simply because, like, isn't this like a calculation people do in high school physics? Like, yeah, like, you know, conservation of momentum, those sort of things. Why was it different to what was expected, I suppose?
I guess we didn't really know much about the momentum and what the momentum would be and what it would do. So for the exact measurement, the spacecraft was speeding in at 23,760 kilometers per hour.
Wow.
And it had traveled essentially like a safe distance of about 11 million kilometers away from Earth. So it traveled this long distance. It was going in that speed, but we don't actually really know still what this asteroid is made of. We didn't know exactly how, when it hit, what would happen. So this is the first time we actually could get a clear image of what the asteroids look like up close and what would actually happen when spacecraft whacks it. So essentially the spacecraft was sending back to Earth one image every single second until it crashed into Dimorphos. And as DART beamed photos back, scientists first got their first close-up look. So essentially, if we look at this system from Earth, they just sort of appear as a single dot in a field of stars. Both asteroids together just appear kind of as one because there are so many stars around and they're very, very bright. But these images snapped by DART, it's really cool because essentially you see it coming in and it's first like an egg-like conglomeration of rocks and then a field of boulders and then gravel and then dust and then impact.
I was at work when it hit, and I don't know, there was someone walking past and said, kind of, what are you doing? I said, I'm looking at a spacecraft hitting asteroid, come and watch. And made them sit down and, yeah. I narrated, of course.
So that alone, I guess, is the mission's first success. But now the whole world is watching as all these telescopes, both on Earth, and then we've got, the Hubble and the JWST that are like looking at what happened before and what happened after. And I think this is an incredible feat as well, because the James Webb Space Telescope was looking at this asteroid and it has to track this asteroid. But the problem is the asteroid is traveling much faster than what this telescope was designed to track. So the team had to kind of work out a new method of capturing what was happening. So the fact that it can is an exciting thing in itself. But having a look, scientists can now see images of before and after impact. And there's now this crater where the spacecraft whammed in. But there's also just this incredible stream or spray of debris that's flying out. And so, like I said, we don't really know what the asteroid is made of. And so now with all of these telescopes around the world and also these two in space looking, it's really showing you the power of collaboration. They're all sort of trained on here looking in visible light, looking in non-visible wavelengths of light, and kind of looking at these dust clouds and the distribution of particles as matter was really just ejected out of Dimorphos.
Okay. Wasn't there I heard there was another Italian satellite or something that was accompanying it too, that was supposed to send back some data? Do you know if we've heard anything from that? I
don't think we have heard from it, but yes, you're right. And we're sending more things out. So yes, the Italian Space Agency is sending out something, and the European Space Agency is also going to launch a follow-up spacecraft called Hera.
Fantastic.
Yeah.
Oh, that's really good, because it's like what you said, that kind of collaboration of everyone working together, like an international collaboration, because I guess we're protecting the Earth here.
Yeah.
So we've all kind of got a stake in it.
Absolutely. We all kind of have a responsibility of protecting our own planet.
Yeah.
Yeah. So it's really exciting to see, all humans kind of banding together and this is kind of one for the dinosaurs. And I know that there are a lot of comments about that when we finally made impact.
Yeah. It's interesting too that you talk about the, I guess, the spray coming out, because I ask, how isn't this just like, say, a high school physics collision thing? But I guess if you got stuff being blown off, we don't know, so we didn't know how massive it was, because we don't know what it's made out of. Then you've got stuff being blown off it, then it's not a straightforward elastic collision, or even an straightforward kind of where it sticks to it sort of thing, because you've blown the bits off it.
Yeah.
You've changed the dynamics. It's kind of a plume. You've changed its mass. You've got a rebound from the stuff being shot off it. You've got a bunch of other effects going on.
Yeah, absolutely. There's sort of this spray of rays if you look at the images, and it sort of just fans out in the direction of the strike. But there's also this really long tail of debris that stretches 10,000 kilometers.
Oh, wow.
Yeah, it's a really, really long just spray of stuff that's come out of this asteroid. And this sort of, there are newer photographs that have come out and shown that this tail has split in two, and scientists are still trying to determine why is there now a fork? How did that tail sort of just split? And Nancy Chabot, who's the coordination lead for DART at the Johns Hopkins Applied Physics Laboratory, says that the tail's spectacular, and this amount of ejector, so that stuff that has been ejected, that we're seeing, it's constantly evolving.
I suppose it's this is the other interesting thing, that we are actually then finding out more about the asteroid itself, and we've sent things up before to take samples of asteroids, so we've had some of that going on before, but this is now we've actually really dug into one and broken it open essentially to see what's inside, what's next? I guess what do you think what are they looking for? What do they expect to find?
Well, I don't know what they expect to find. I think it's everyone's sort of just watching this new data come in every day, and astronomers are going to be better able to assess, whether or not a mission like DART could be used in the future to protect Earth, but also what can we get from asteroids? As you say, we don't know exactly what's in it. And I know that we are running out of particular resources on Earth, like minerals, and NASA does want to mine things like platinum and gold and other precious metals that are sort of running dry here. Could we get them from asteroids?
Yeah, and I guess also interesting questions like, did we get water from asteroids? Could asteroids transmit the ingredients of life and those sort of things? So finding out what's inside them is because they're often like relics of the early solar system, and they carry that have been just floating around for billions of years. So they carry kind of that time capsule of the ingredients for everything.
It's just a bit of history.
Great.
So he's hoping that space agencies can be ready for whatever the universe throws at us.
Well, thank you, Katrina.
I think we're lost.
We're not lost.
Not even any short-range radio signals yet?
Except for a single, very powerful radio emission.
Of course, a transmitter of that sort isn't exactly standard equipment.
Science and technology must be absolutely mind-boggling.
Of course, it's mostly on the theoretical side.
Well, so far.
Across Australia on the Community Radio Network, you're listening to Lost in Science.
So I don't know if anyone has been paying attention to the renewed interest in returning to the moon, getting people back on the moon. We last went probably, I think almost 50 years ago was the last, human landing on the moon. But people are talking about it. All sorts of different countries are talking about going back to the moon. But one of the things about the moon is there's not really a lot there, which is one of the reasons we stopped going. There's no plants, there's no animals, there's just a big, empty, barren surface. And we've kind of looked at that a little bit. But when people are planning to go back to the moon, they're kind of thinking of maybe staying a bit longer. In that case, they need to make it a bit more hospitable for people to live there. And people have other needs than just oxygen and food and water. They also need a nice environment to live in. Now, I have got Dr. Tien Huynh from Applied Sciences at RMIT, who is going to talk with me about the idea of growing plants on the moon. And thanks for joining us on Lost in Science, Tien.
Thanks for inviting me, Stu, and it's exciting to tell you about our project.
So what is the big idea here? What is the point in growing plants on the moon, and why has someone thought of this idea?
Well, it came from our engineer, Dr. Graham Dorrington, and he's an engineer who wanted to create a terrarium type structure, so shoebox size, that we wanted to send to the moon, and he wanted to know whether we could actually contribute towards life on the moon. It's really interesting. There's been so many people involved, from engineers to we've even gone to 3D printing and a whole load of IT people. So it's so we've got a manufacturing precinct that builds like from small 3D printed stuff to big house 3D printed stuff. So they've been really great. And everyone, when we talk about this little shoebox going up in space, they're like, oh, what can we do? But there are obviously quite a lot of issues in terms of challenges to getting plants to the moon. So we have about a 4.5-month orbit from Earth up to the moon and goes in transit around the moon before it actually lands on the surface, where it faces a lot of harsh conditions, the sub-zero conditions, and that's not really conducive for plant growth. So we wanted to work together and create this little chamber that was actually going to achieve those purposes. So we wanted to put it with the astronauts and see if it can survive the mission in terms of these low temperatures, as well as harsh variations, so heat, cold, as well as zero gravity conditions. And then it has to germinate really quickly while the astronauts are there. So we had a 24-hour limit in terms of how can we make these plants or seeds grow within 24 hours. So that was the challenge, and the engineers and I went together and we decided to build things ourselves to make that prototype to send to the moon with our astronauts.
So how did you go about, and you're saying you've got very limited time to get the plants to germinate and all this sort of thing. How, all the plants we know of have evolved on Earth. Where did you go looking for plants that could potentially survive the journey and survive on the moon? Where did you first look for plants?
Well, we looked to home. So Australia is really known for very harsh dry, arid conditions. So we have one of the plants that we've chosen is an Australian native grass, so it's a resurrection plant. So it can go to below 5% moisture content, and then once it has water added to it, it will come back to life, flower and then fruit within less than a few days, so 2 days. So we know that there's plants that in Australia that can do this really well because we've got such harsh climates, and we wanted to replicate that in terms of putting that theory in terms of these harsh conditions and see if that can be assimilated on the moon. We also looked at seeds that we use, so crop plants that we eat and use economically on Earth, to see if that could be also used. So not just seeds that can germinate, but also plants that can be resurrected. So we looked around us, and Australian Indigenous plants, for instance, was one of those inspirations that we had to see if we can actually, see if they can survive in those conditions. And one of the key findings that we wanted to get out from that was replicating those mechanisms that helps them to survive harsh conditions, like on the moon and the travel, to see if we can fast track a lot of the challenges we have on Earth for food security, as well as for challenging environments that makes plants unable to grow here on Earth.
So some of this work could be really useful in figuring out how to get plants to grow back on Earth as well. So in harsh environments that we, we've got a lot of empty space in it. Well, it's not empty space, but we've got a lot of space in Australia, which is not, not highly productive land and that sort of thing because of the harsh conditions. Will this research kind of inform that and help us to grow things in those harsh environments here as well?
Absolutely, because we do a lot of, so the biology team have a lot of genomic and proteomic experience. So we do a lot of technology things to figure out what genes need to be there, what needs to be activated, what are the stimulants. And by knowing more about these harsh conditions on the transit to the moon as well as on the land, on the moon surface, we can actually replicate some of those things that are stimulated on Earth, where plants do struggle in these different climates, both for drought, flooding, fire, all sorts of events that we're seeing now, because we believe that nature has all the solutions. And that's where the genes in these plants, it just depends on the stimulant. So we want to know what is it that we can do for plants on Earth to make them survive better and grow better and do the things that we want it to do. So we can benefit from it.
So you're trying to figure out what are the triggers that make the survival genes kick into action is what you're looking for. Now, one of the things I am curious about, though, is so on Earth we have, what we would consider normal gravity, and all the plants that we've got are in normal gravity. Now, the moon is a lot smaller than the Earth, so it has a different level of gravity. How do we think that's going to affect plant growth when they get onto the moon?
Well, there are some studies that have shown that gravity, because we do have anti-gravity machines on Earth that we can simulate that. And that didn't seem to be too much of a factor when we did our preliminary trials. It was more about the extreme temperatures that the plants will face. Now, we know with stratification, for instance, with seeds, we do make plant seeds go dormant under low temperatures, and that's for in case extinction events happen. And we have seed banks on Earth in case we're hit by an asteroid, and where we actually put these plants in sub-zero conditions and keep them dormant in hibernation until we add the right temperatures or stimulants to make them grow again. But it's the extreme shifts, so from very low temperatures to very high temperatures, that causes a lot of the viability to be reduced. And so that's what we want to actually know more about in terms of these unstable and variable conditions and what it has, the effect it has on vegetation for both seeds and plants.
Another thing that occurs to me that's quite different on the lunar surface compared to on the Earth surface is the amount of light that's available. So a day on the moon is not the same as a day on Earth. It's not 24 hours long. How's that going to affect the plants?
Well, that's why our little shoebox, or we call it the lunarium, is going to have not only sensors but also lighting and satellites to beam back the images real time back to Earth. So we've also got simultaneous experiments with high schools, and I'd encourage, if you want to get involved, Stu, maybe even take students to actually have simultaneous experiments on Earth once we have the prototypes. So the shoe boxes that we're going to send out to schools so they can actually be involved and get students or people on Earth to be interested in what's happening on Mars and on the Moon. And hopefully it will generate a lot more interest in people looking at germination and resurrection of plants in harsh conditions.
So I guess students might be much more likely than older people to actually even get to the moon at some point. But so when the plants are in their lunarium on the moon, are they growing in? What are they growing in? What's the growing media that they'll be growing in?
Well, we've got different types. One is like a rock-like substrate that's meant to replicate the moon, but we've also had challenges in terms of the box that we can send up. It has to be a certain dimension, a tiny little thing, as well as has to be very low weight. So one of the other things that we're going to do is also have it in like a media, an agarose type mix where it has all the nutrients that's needed. But that's also challenging because we don't want it to be in water, because water will freeze during the mission when it's flying up. So we've had to rejig a few things, and we can't really tell you too much about it, but those have been one of the challenging things that has come up.
It's a
secret. Great question, Stu.
It's a secret formula, is it?
And it's always changing because we've had lots of variations in terms of weight that's allowed, dimensions allowed, as well as the electrical currents that's allowed. So everything has to be fully contained in the box. And so we've had to change according to what's required based on the astronauts' advice.
And one of the other things I was thinking about too, because I've got a horticultural science background, is that on Earth we've got plants growing in natural soils, and a lot of the plant nutrients that the plants in natural environments use get recycled all the time. And I know you have got some experience of growing combinations of organisms in culture. You growing orchids with different fungi in aseptic cultures, in sterile cultures, with just those things you've added. Without those other organisms, without the microbes and the bacteria and the fungi, the nutrient cycling can't really take place. So in a longer term project, would you look at expanding it to sort of get mini ecosystems going in your lunariums as well as just the plants?
It's a good idea, but at the moment we really want to focus on the water content, not so much nutrients, only because we don't want to leave too much debris on the surface. We want this to come back to Earth, so the less we put up there, the less we bring back. Makes it easy for everyone. So that's been what's in conversation at the moment in terms of what can we put up there, minimise the input that we have to send up, but increase the output that we get in terms of the information.
And also, I guess there is possibly an issue of contamination. You don't want to leave,
Correct.
Microorganisms lying around on the moon for later, because who knows what they might change into while they're there as well.
Correct.
It sounds like an amazing project, and I'll put up some links to the project on our webpage with our podcast. But I'd just like to thank you again, Tien, for joining us on Lost in Science. Sounds like an amazing project, and we'll stay tuned for more info.
Thanks, Stu, and looking forward to seeing this project literally launch off.
And that's it for another episode of Lost in Science. Lost in Science is recorded for 3CR in Melbourne on the lands of the Wurundjeri people of the Kulin Nation, and it airs across Australia on the Community Radio Network with the support of the Community Broadcasting Foundation. We would love you to get in touch with us. You can email us at lostinsci@gmail.com, or you can find us on Facebook, we're Lost in Science on 3CR, or on Twitter, where we're at Lost in Science 1. You can find us on your favourite podcast app, where if you get the chance, please give us a good rating and review, as that will raise us up in the search rankings so other people can find the science. Or you can listen to us however you listen to us now. We're the same time every week when we all get
Lost in Science.
Thanks for listening to a 3CR podcast. 3CR is an independent community radio station based in Melbourne, Australia. We need your financial support to keep going. Go to www.3cr.org.au for more information and to donate online.